Hi everyone, in this video we will have a study of flyback converter, and the first thing we should know is that the flyback converter is derived from the buck boost converter. So how does this thing happen? It's very easy. This is a buck boost converter, and the first step is we split this inductor into a transformer, and then we split this transformer into primary and secondary, and the last step is we move this switch to lower side to have a low side switch for easier driver and control. Also, we change the positive sign of primary side and secondary side, so the converter now is not inverting. The sign of input power and output power are same. Why we do this is by doing this we make the converter galvanic isolation. It means we use different ground between inputs and outputs, and also because we are using the transformer, we can make a higher conversion ratio of voltage. The flyback converter have a lot of common with buck boost converter. So in this video, I will point out the difference between these two kind of converter. So if you have a good understanding of buck boost converter, it will be very easy for you to learn flyback converter. This is the topology of our flyback converter, and we do the same analysis as other converter. Is we first plot the on state and off state circuit. This is our on state and this is our off state flyback. One thing I should point out is this inductor is not a real inductor. It's the magnetic inductance of our transformer. Okay, let's first still analyze the CCM mode. The same thing as the other converter is, first of all, we look at the inductor. So we first plot the voltage waveform and current waveform of the inductor. This is the voltage waveform of our inductor, and when the converter works in on state, the voltage on inductor is Vin, and when it's in off state, we can use the secondary side to calculate this side. So the voltage on the inductor is minus Vout divided on N. Using those values, we can easily have our on-state equation is delta IL equals to V in times T on divided on L, and our off-state is delta IL equals to V out times T off divided on NL. By using these two equations, what we can get is same as buck boost converter. First of all, we can know the voltage conversion ratio. We make this on-state delta IL equals to off-state delta IL. We can get our V out divided on V in equals to N times D on 1 minus D. The only thing different from the buck boost is we have to times the winding turns ratio here. The winding turns ratio is 1 to N here. The second thing is we can calculate the delta IL, and it's same here. We already know our delta IL equals to V in times DT divided on L, and the offset is a little bit different because our V out is using V out divided on N. So our delta IL on off state is V out times 1 minus dt divided on NL. And the third thing we can know is our average inductor current. This one is same as buck boost. We still use the input power equals to our output power, and our input power is V in times I in, and output power is V out squared divided on R. So we have the exactly same average inductor current as buck boost is V out squared divided on V in times RD. And you may have to ask, the value should not be same as buck boost because we use a transformer, and where does this transformer times ratio show in this equation? Is that I use V out and V in here on purpose, because by using this, you are actually only remember the same equation for both flyback converter and buck boost converter. But the value is different because we have N times onto the voltage conversion ratio. So this is where the N shows in this equation. After we analyze the inductor, we now analyze the capacitor. Because the secondary part is exactly same as buck boost, we didn't change anything when we derived the flyback converter, so everything is same as buck boost converter. So our delta V out is D times V out divided on RCF. Okay, so this is all we can know from analyzing the CCM mode. And now let's move to DCM. The boundary of CCM and DCM is same as all converter, which is when our average inductor current is equal to half of the inductor current ripple. Let's plot the DCM inductor waveform here. This is our inductor voltage and current waveform. Same as CCM, when the converter working on state, the voltage is V in, and off state it's minus V out divided on M. We know that the DCM mode happened because there is not enough energy stored in inductor, so at some point in the off state, the current went to 0, and we don't know when this happens. When we calculate the delta IL, we can only use the on-state formula. So delta IL can only equal to V in times dt divided on L. And our average inductor current is same, so it's average inductor equals to V out squared divided on V in times RD. And we know that when the DCM mode happens, the voltage conversion ratio is different. So our I in equals to the average value of our switch current, and is delta IL dt divided on 2t. So we can have our V out divided on V in equals to dt times square root of R divided on 2LT. And this is same as buck boost, but because we use a transformer, so we don't have the inverting. So this means we don't have the minus sign here. And the last thing we want to know in our DCM is we want to know our critical resistance. This means that when the load is higher than this value, our converter works in DCM mode. So by using this boundary, and we can calculate our critical resistance is equal to 2M V out L divided on V in times dt times 1 minus d. And again, this formula is very similar to buck boost, only we need times of n here. So this is all about flyback converter. So what formula we should remember is first the voltage conversion ratio in CCM, and you can either choose to use the on state or the off state to calculate the delta IL and how to calculate our average IL and our output ripple relationship with the capacitance. And in the DCM mode also, you can only use the on state to calculate the delta IL. The average inductor current is same as CCM and also same as our buck boost converter. Our voltage conversion ratio is different from our CCM mode, but this formula is same as our buck boost converter. And our critical resistance value is calculating using this formula. Alright, so let's do this flyback converter problem together. This flyback converter have an input voltage as 48 volts, and the input voltage can floating from 48 to 54, and our output voltage is 380 volts. The nominal load resistance is 722 ohm, and the switching frequency is 100K. The current ripple is 1 amp and the voltage ripple is 1.9 volts. The first question asks us to design the winding turns for the flyback transformer. Based on the output voltage is 380, divided on our input is 48 volts, we can get value as 7.9 something, and I will pick n equals to 6. You can also pick a number that's close to this value. The second question asks us to calculate the duty ratio when the converter work in CCM mode. For our input is 48 volts, our D is equals to V out divided on MV in plus V out equals to 57%, and for V in equals to 54 volts, our duty using the same equation we can get is 54%. The third question asks us to design the inductance and the capacitance to make the ripple lower than the specification. We also calculated based on different inputs. When the input is 48 volts, our inductance equals to V in times dt divided on delta IL, and we can have the value is 137 microhenry. Our C out is equal to dV out divided on total V out times RF. We got 1.6 microfarad. And for our input is 54 volts. Our inductance in the same equation is 146 microhenry, and our capacitance is 1.5 microfarads. And we pick the larger size as our design value. So for our inductance, we pick 146 microhenry, and for our capacitor, we pick our capacitance as 1.6 microfarad. The fourth question asks us, when our input is 50 volts, what's our critical resistance? We use this formula, 2N times VL times L divided on V in dt times 1 minus D, to calculate the critical resistance. The only thing we don't know in this equation is we didn't calculate the duty when we do it in question 2. So now we calculate the duty by using D equals to V out divided on MV in plus V out is 56%. We put this value back in here, and we got our critical resistance is 5,403 ohm. The last question asks us to calculate the output voltage when the load resistance is 10K and the input is 54 volts. We first need to calculate the critical resistance. Under this condition, the critical resistance using the same formula in question 4 we can get is 4,963 ohm. V out equals to V in times dt times square root of R divided on 2LT. We got our output voltage is 499.66 volts. Alright, so this is all about this video. We will see you in next video.